Hi students, in today's session we are going to discuss about the stability of a nucleus. In addition to that, we are also going to discuss about the topics mass defect, binding energy and binding energy per nucleon. So let us begin with what is a stable nucleus. A stable nucleus is one which has a minimum energy. Now, all combinations of protons and neutrons, as you all know, a nuclei contains protons and neutrons, and all combinations of protons and neutrons do not correspond to a stable nuclei. In light nuclei, we see that light nuclei, majority of the light nuclei are stable when their number of protons is equal to the number of neutrons. By light nuclei, we mean those nuclei whose atomic number is less than 20. അതായത് ആറ്റമിക് നമ്പർ ലെസ് ദാൻ 20 ആയ ലൈറ്റ് ന്യൂക്ലിയകളിലെല്ലാം തന്നെ അവരെ ഏറ്റവും സ്റ്റേബിൾ ആയി കാണപ്പെടുന്നത് അവരുടെ നമ്പർ ഓഫ് ന്യൂട്രോൺസും പ്രോട്ടോൺസും ഈക്വൽ ആകുമ്പോഴാണ്. ദാറ്റ് ഈസ് Z is equal to capital N. Here Z represents the atomic number, which is the number of protons, and N represents the number of neutrons. But for heavier nuclei, they are found to be more stable when the number of neutrons is greater than Z. That is, for those nuclei with atomic number greater than 20, they are found to be more stable when capital N is greater than Z. Now, a plot of N versus Z is shown here. That is, number of neutrons on the y-axis, number of protons or atomic number on the z-axis. It is found that for lighter nuclei, that is Z less than 20, they exist when these nuclei exist in a stable condition when number of neutrons and protons are equal, and as the atomic number increases, that is, as the number of protons increases, the heavier nuclei, that is, for the heavier nuclei, they are found to be stable when their number of neutrons are greater than the number of protons. See here, when the number of neutrons is 30, in this particular stable nuclei, we find that the number of protons is less than 30. Again, when the number of neutrons is nearly 40, it is found to be stable when the number of protons is less than 30. So we see that for heavier nuclei, they are found to be stable when the number of neutrons is greater than the number of protons. Next, we just conclude once again. Thus, in a stable nuclei, either N tends to be equal to Z in a lighter nuclei, or N is greater than Z in a heavier nuclei. Now, the tendency of N to follow Z is because in the nuclear energy, energy levels, the nucleons with spin half obey Pauli's exclusion principle. That is, we are going to discuss how the protons and neutrons are arranged in the nuclear energy levels and what is the reason for their stability or instability. So, protons and neutrons are fermions having spin half, and they obey Pauli's exclusion principle. Now, each energy level, that is, each nuclear energy level, will have two protons and two neutrons. And these neutrons and protons in an energy level should have opposite spins. That is, a particular nuclear energy level will have two protons of opposite spin and two neutrons of opposite spin. Now, the energy levels are filled in a sequence in order to attain minimum energy and maximum stability. Now, if an unpaired neutron or electron is present in a particular energy level, then it will decrease the stability. Now, you can look here. I have shown the filling of boron 512 and carbon 612. That is, both are having 12 as their mass number. That is, total number of nucleons in both these cases are the same. But boron has 5 protons and carbon has 6 protons. Now, by filling the nuclear energy levels, we can see that boron has more energy and is less stable than carbon. Let us see how. See, boron has 5 protons. That means boron has 5 protons and 7 neutrons. So, let us see how they are filled. So, in the first nuclear energy level, you fill 2 neutrons opposite spins and 2 protons opposite spin. Second energy level, again 2 neutrons of opposite spin, 2 protons of opposite spin. Third energy level, but you have only 5 protons there. So, only 1 proton will be there, and there will be 2 protons because the 2 neutrons because the number of neutrons is 7. And in the next energy level, you have the 7th neutron with a particular up spin arranged there. So you see there is an unpaired neutron here, there is an unpaired proton here. That means unpaired nucleons increase the energy and decrease the stability. Whereas in carbon 12, you have 6 protons. If there are 6 protons, then 12 minus 6, there will be 6 neutrons. So you arrange 2, 2 protons and neutrons of opposite spins in each nuclear energy level, and there are no unpaired protons or neutrons here, thereby increasing their stability. That is, this is a minimum energy condition because there is no unpaired electron and it corresponds to maximum stability. Thus, boron and carbon, though both of them have 12 nucleons in the nucleus, boron has lesser stability than carbon. Next, we told that in heavier nuclei, the number of neutrons are found to be greater than number of neutrons for the nuclei to be stable. Now, why is it so? Now, protons are positively charged and they repel each other. Now, this repulsion becomes more or greater as the number of protons become larger. Whereas neutrons produce some kind of attractive force, and an excess of neutrons in the nucleus will thus correspond towards the required stability. That is why we say that the number of neutrons must be greater than the number of protons in the nucleus so that a heavy nucleus will be more stable. Now, even in lighter nuclei, though in most of the lighter nuclei number of neutrons and protons are equal, there may be some cases where the number of neutrons exceed the number of protons. But the inverse is very rarely true. That is, the number of protons being greater than the number of neutrons is true only in the case of hydrogen H11 and helium He23. In all other cases, in the light nuclei, either capital N is equal to capital Z or N is greater than Z. Next, out of all the stable nuclides, about 60% are even nuclides. That is, even number of protons and even number of neutrons. Nearly all the others are even odd or odd even nuclides. Even odd means even number of protons and odd number of neutrons, or odd even means odd number of protons or even number of neutrons. Only 5 stable odd nuclides are known. Examples of odd nuclides. Odd means odd number of protons and odd number of neutrons are H12, lithium 36, beryllium 510, nitrogen 714 and terandulum 73 180 are the only stable odd nuclides. Now, nuclear strong forces are strong range forces and they affect only their nearest neighbors, and this effect is called saturation. Now, the heaviest known stable nuclide is bismuth 83209. All nuclides with atomic number greater than 83 and mass number greater than 209 are unstable and they spontaneously undergo alpha decay and become lighter nuclei. Here I am giving you an example of alpha decay, how the alpha decay takes place, which we will be dealing very well in detail in our later chapters. So I just told here that nucleides with a number of protons greater than 83 and total number of nucleons greater than 209 will undergo alpha decay and become lighter. Okay, so how does alpha decay take place? Zxa is equal to an alpha particle, that is a helium nucleus is given out. That means helium has atomic number 2, mass number 4. So the daughter nuclei will have atomic number Z minus 2 and mass number A minus 4. So that this equation is balanced. So you get a daughter nuclei having a smaller number of protons and a smaller mass number, and this will be more stable than the parent. Now, to attain the appropriate neutron to proton ratio, the daughter nuclei may also undergo beta decay. Beta decays are of two types: negative beta decay, positive beta decay, or it can be an electron capture. Here I have given you the equations for how a negative beta decay takes place, where a neutron gets converted to a proton, releasing an electron and an antineutrino, and positive beta decay where a proton gets converted to a neutron and a positron with the release of a neutrino. And electron capture is the combination of a positron and an electron to give a neutron and a neutrino. All these are methods by which the nucleus attains stability. Next, we go on to binding energy and mass defect. What is mass defect? It is the difference in mass between the mass of the nuclei and the sum of the mass of the nucleons. Here we find that the mass of hydrogen H11 nucleus is 1.0078254 and that of a neutron is 1.0086654 and that of hydrogen H12 is, that is deuterium. Deuterium is 2.0141024. But when you check, you find out that when you add the masses of this hydrogen nucleus and neutron and subtract from it the mass of the deuterium nucleus, we find that there is an excess mass of 0.023884. And this mass, this difference in mass between the sum of the mass of the nucleons and that of the mass of the nucleus is called mass defect. Now, this mass defect corresponds to an energy given by delta E is equal to delta M into this mass is given in AMU, and we know that 1 AMU corresponds to 931.49 MeV per AMU. So, the energy corresponding to this mass, that is delta M mass, is given by delta E is equal to delta M into 931.49, which is 2.224 MeV. The energy equivalent to this mass defect or energy equivalent to the missing mass is called binding energy. That is, the energy corresponding to the missing mass is used to hold the nucleons together in the nucleus. That means an energy of 2.224 MeV is required to break apart the deuterium nucleus. If we say that this much energy is required to hold the nucleons together, it means that this much energy must be supplied to break apart the deuterium nucleus. So, here we define binding energy. Binding energy is the energy required to break apart a nucleus into its constituents. It is the energy required to break the nucleus into its constituents. So, how do you calculate the binding energy? To find the binding energy, you find out first the mass defect, that is the mass of a proton into number of protons plus mass of the neutrons into number of neutrons minus the total mass of the nuclei into 931.49 MeV will give you the binding energy. Next, what is binding energy per nucleon? The total binding energy of the nucleus divided by the total number of nucleons will give us the binding energy per nucleon. So for hydrogen, the binding energy per nucleon is 2.2 divided by 2. Sorry, it's not for hydrogen, it is for deuterium. H1, 2. It must be 2 here. That is why we divided here with 2. So the binding energy per nucleon for the deuterium nucleus is 1.1 MeV per nucleon. For bismuth 83209, that is the heaviest known nuclide, it is 1640, which is binding energy of bismuth, divided by 209, which is 7.8 MeV per nucleon. And for the most stable nuclei, which is iron 2656, the binding energy per nucleon is found to be 8.8 MeV per nucleon. Next, we discuss the graph of binding energy per nucleon versus mass number. Here we find that the binding energy per nucleon increases as the mass number increases. It reaches a maximum value for iron 2656, and then the binding energy per nucleon decreases. That is, for lighter nuclei, the binding energy per nucleon is less, and for as the mass increases, as the mass number increases, the stability or the binding energy per nucleon increases. A larger binding energy per nucleon corresponds to greater stability. And as the mass number increases, the binding energy per nucleon decreases. That is, as the size of the nucleus increases, the nucleus becomes less and less stable. So light nuclei are also less stable and heavy nuclei are also less stable. That means light nuclei can undergo nuclear fusion. That is, two light nuclei can join together to form heavier nuclei and they can become stable. And the heavier nuclei can disintegrate by fission, by nuclear fission, and they can become a stable, lighter nuclei. In both these cases, large amount of energy is released. So this is the very, very important binding energy per nucleon curve plotted against mass number, which shows that the lighter nuclei are less stable and heavier nuclei are also less stable because they have low binding energy per nucleon. So a lighter nuclei attains stability by undergoing nuclear fusion with the release of large amounts of energy, and the heavier nuclei becomes very stable by forming, by disintegrating to form a stable nuclei with, with the release of large amounts of energy. So I just give out the binding energy for the binding energy per nucleon curve is shown here. So the implications or the two important conclusions that you get from the above graph is when a heavy nucleus with low binding energy per nucleon splits into lighter nuclei, the difference in energy is given off and this is called nuclear fission. And an example is shown here. And when two light nuclei combine together to form a heavy nucleus, again, the nucleus becomes highly stable and a large amount of energy is given off and this is called nuclear fission. So I hope this session, which included the discussions on stability of the nucleus, mass defect, binding energy and binding energy per nucleon with special reference to binding energy per nucleon curve is clear to all of you. If you have any doubts, please do contact. Thank you.